Hello, everyone. My name is Yuan Hu. I'm a postdoc at Merck in Department of Chemistry, Modeling, and Informatics. Thanks, Mike and Romy, giving me this opportunity to speak on behalf of Merck DCR team. So today I want to talk about MD simulation in pose refinement and scoring using Amber workflows. As a Merck DCR team, we participated both stage 1 and stage 2. Since we have a better result in stage 1, so today I'll just talk about the stage 1 result. The outline of the talk will be as follows. First, I'll give you an overview of the DCR predictions for Merck and the overall post prediction and scoring approaches. And then I'll follow by the case study and some lessons we learned. First, I want to thank all the Merck DCR team members. The team includes scientists from both modeling and informatics groups across multiple Merck sites. We are highly motivated to take this opportunity by participating in the DCR Grand Challenge to refine and share our best practices, and also to be engaged in the scientific community and to better understand the capability of science in the field. For step 1, we took the following approach. In step 1, we prepare all the structures as a team, where we took the 102 DCR dataset and did literature search and data mining, and then we prepare the structure using Schrodinger's tools. We want to start at the same point. So at step 2, we did the individual docking experiments, which includes the glide ensemble docking, colonial entropy docking, glide and go docking, and visual inspection. And for each experiment, we make individual submissions. So in step 3, we want to further test the MD power. So we took the glide ensemble docking, the top scoring pose, and carried out MD simulations using multiple replicates. We further refined the MD pose and also did GBSA ranking score. In today's talk, I will focus on 2 questions. The first, can MD be used to refine the docking pose? And second, how does MD GBSA perform in the ranking? Well, long story short, MD simulation, from our submissions, it do shows that it can improve the pose prediction and also ranking. Where we start from the ensemble docking result, you can see the result is actually improved. So how we did it, we have a fully automated glide ensemble docking workflow and Amber workflow to carry out the experiments. Where we did ensemble docking and using glide XT, and we took the top screen pose and then carry out the MD GBSA workflow, where we use 20 replicates. For each MD simulation, we run equilibration and production. And for the production result, we use it for GBSA analysis. And also we build a web interface and also include command line script can enable us to automate all the calculations. And it also enables us to do the calculation on Korean GPU. For the production trajectory, we further took those trajectory to generate the poses based on the structure or based on the average structure or the lowest free energy snapshot or the components. Or also at the last one, we also took the highest population cluster generated by using the structure similarity. As a first lesson learned from the docking, the good template is always important for docking. As shown here, a similarity cutoff of around 0.5 is found. As shown here, the first 4 chemical series with the similarity less than 0.5, we didn't get any good docking poses, or most of the poses have a larger RMSD value. But interestingly, for the benzoimidazole theory, we found that actually it can overcome the similarity problem. where for the lower similarity compound, you can still get a very good poses. I think the major reason is because we have a lot of template structure available for this theory. And another interesting thing we found is that for the first four theory, for the lower similarity compound, they are usually correlated with a very inactive compound, where the activity showing colored in red is larger than 1 micromolar. So for the first question we want to ask, can those MD methods be used to refine those docking poses? As shown here, the MD simulation do show this power. It can maintain the poses if it's below 2 angstrom. So here we use a cut of 2 angstrom to consider a good pose, and 4 angstrom to consider a pose whether it is random. And it can further conform the structure and maintain the good poses. And for the poses between 2 to 4, it actually could improve the poses. And for poses is random is actually the MD cannot help too much to refine the pose. Here I'll give you a couple of case studies. And for compound FXR3, in crystal structure, there is a continued tyrosine interaction, the hydrogen bond interaction. And in the docking pose, we didn't capture that interaction. Well, by using MD, it do refine the structure and move the ligands to create the stable hydrogen bond. With the MD refinement, it do bring us to the top 1 for this pose prediction. And for the second case study, FXR10, this compound in crystal structure, there is a carboxylic acid asparagine in hydrogen bond interaction found in the crystal structure. Well, in the docking pose, our template is having the asparagine side chain in a different direction, which didn't create this hydrogen bond interaction. By using the MD simulation, it do reorient and the asparagine to make this hydrogen bond contact and optimize the protein structure to generate a better pose, which, well, we are standing in the second place for this compound prediction. Well, there are some cases MD cannot really help. The first one I want to talk about is FXR15. This compound is quite symmetric when looking at the crystal structure. Well, the docking pose, we have a pose with a reverse direction compared to the crystal structure. By using MD, it's actually very hard to refine the structure with those wrong directions. And we got the pose is actually not so good. I would say it's also, it's surprising we're not the last one. They do have a couple of good poses. I do want to hear how they got the result. And another case is FXR18. The MD workflow cannot address actually a very large protein movement. In this case, we found the template we use is have a large chain movement compared to the crystal structure, which is shown in the cyan color. By using MD, it further opens up the chain or the pocket. And this compound turned out to be a very challenging compound, where you can see about almost everyone got the pose is larger than 2 angstrom. Okay, so switching to the ranking, there are some lessons learned from the previous DCR challenge, like explicit solvent free energy method have not yet outperformed the faster scoring method. So here we have a question, so how does this MMGBSA method perform? By looking at the docking method, the glide ensemble docking do shows a good correlation compared to other docking approach or single snapshot MMGBSA calculation using the stage 136 compound. So we took the same poses from the glide docking structure and did MD and MMGBSA calculation. The correlation do actually improve. Here I want to say it's not the best one. Is there have some challenge. It's actually a challenge data set for implicit model because the bonding side is actually very deep inside for this target. So maybe in future, some other solvent model or more rigorous calculation like a TI or FEP may further improve the accuracy. As a summary, we have several lessons learned from this challenge. First, the ensemble docking do perform very well in pose prediction and also ranking. The MD simulation can actually maintain or refine the docking pose through the protein or ligand interaction and also extend the limit of the prediction. But MD cannot refine very challenging poses, such as reverse direction or large chain movement. And third, the ensemble-based MD MMGBSA ranking approach improves on the docking scores. And our last one, we work in the team, and the teamwork to break the challenge down to a manageable portion. And we prepare things together, and also by using the same starting point, it allows us to test many methods and do large-scale comparison internally. As another advertisement, we collaborate with Rutgers University on a new GPU code development in Ember. So the code is available for us to test. On the next step, we do want to test the more rigorous calculation like Ember TI, and also moving from the CPU to GPU calculation to make it more fast and accurate. That's all. Thanks for your attention.